Graphene is a one-atom thick crystalline form of carbon in which carbon atoms, held together by strong sigma bonds, are arranged in a two-dimensional honeycomb lattice. Owing to the structure dictated by the sp2 bonds, the only unpaired protruding p orbitals make graphene a semimetal with unusual electronic properties that are best described by theories for massless relativistic particles. Charge carriers in graphene show linear rather than quadratic dependence of energy on momentum, and field effect transistors with graphene can be made that show bipolar conduction. Because of the long-range order imposed by the sigma bonds, charge transport is ballistic over long distances. The material exhibits large quantum oscillations, large and nonlinear diamagnetism. It conducts heat and electricity very efficiently. It is nearly transparent, and about 100 times stronger than would be the strongest steel of the same thickness. Graphene stacked in a three-dimensional structure makes another naturally occurring allotrope of carbon, graphite. A honeycomb structure similar to its own can be recognized in carbon nanotubes. Scientists have theorized about graphene for decades. It has likely been unknowingly produced in small quantities for centuries through the use of pencils and other similar applications of graphite. It was originally observed in electron microscopes in 1962, but only studied while supported on metal surfaces. The material was later rediscovered, isolated and characterized in 2004 by Andrei Jain and Konstantin Novoselov at the University of Manchester, who were awarded the Nobel Prize in Physics in 2010 for their research on the material. High-quality graphene proved to be surprisingly easy to isolate. The global market for graphene was $9 million in 2012, with most of the demand from research and development in semiconductor, electronics, battery energy and composites, and is expected to reach $151.4 million by 2021. History: In 1859, Benjamin Collins Brodie was aware of the highly lamellar structure of thermally reduced graphite oxide. The structure of graphite was determined in 1916 by the related method of powder diffraction. It was studied in detail by V. Kolschutter and P. Henny in 1918, who also described the properties of graphite oxide paper. Its structure was determined from single crystal diffraction in 1924. The theory of graphene was first explored by P. R. Wallace in 1947 as a starting point for understanding the electronic properties of 3D graphite. This level is responsible for the anomalous integer quantum Hall effect. Further graphene research: One of the very first patents pertaining to the production of graphene was filed in October 2002 and granted in 2006, U.S. Pat. 7,071,258. Titled Nanoscaled Graphene Plates. This patent detailed one of the very first large-scale graphene production processes. 2 years later, in 2004, Andrei Jain and Kostya Novoselov at the University of Manchester extracted single-atom thick crystallites from bulk graphite. They pulled graphene layers from graphite and transferred them onto thin CO2 on a silicon wafer in a process called either micromechanical cleavage or the Scotch tape technique. Two electrically isolated the graphene and weakly interacted with it, providing nearly charge-neutral graphene layers. The silicon beneath the CO2 could be used as a backgate electrode to vary the charge density in the graphene over a wide range. They may not have been the first to use this technique. U.S. Spat. 6,667,100, filed in 2002, describes how to process commercially available flexible expanded graphite to achieve a graphite thickness of 0.00001 inches, 2.5 times 10⁷ meters, or 1/100,000th of an inch. The key to success was high-throughput visual recognition of graphene on a properly chosen substrate, which provides a small but noticeable optical contrast. The cleavage technique led directly to the first observation of the anomalous quantum Hall effect in graphene, which provided direct evidence of graphene's theoretically predicted Berry's phase of massless Dirac fermions. The effect was reported by James Group and by Philip Kim and Yuanbo Zhang, whose papers appeared in the same issue of Nature in 2005. Before these experiments, other researchers looked for the quantum Hall effect and Dirac fermions in bulk graphite. In 2016, Brown University introduced a method for crumpling graphene, adding wrinkles to the material on a nanoscale. This was achieved by depositing layers of graphene oxide onto a shrink film, then shrunken, with the film dissolved before being shrunken again on another sheet of film. The crumpled graphene became superhydrophobic and, when used as a battery electrode, the material was shown to have as much as a 400% increase in electrochemical current density. Spin transport. Graphene is claimed to be an ideal material for spintronics due to its small spin-orbit interaction and the near absence of nuclear magnetic movements in carbon, as well as a weak hyperfine interaction. Electrical spin current injection and detection has been demonstrated up to room temperature. Spin coherence length above 1 micrometer at room temperature was observed, and control of the spin current polarity with an electrical gate was observed at low temperature. Magnetic In 2014, researchers magnetized graphene by placing it on an atomically smooth layer of magnetic yttrium iron garnet. The graphene's electronic properties were unaffected. Prior approaches involved doping graphene with other substances. The dopant's presence negatively affected its electronic properties. Graphene nanoribbons. Graphene nanoribbons, nanostrips in the zigzag orientation, at low temperatures, show spin-polarized metallic edge currents, which also suggests applications in the new field of spintronics. In the armchair orientation, the edges behave like semiconductors. 3D graphene. In 2013, a three-dimensional honeycomb of hexagonally arranged carbon was termed 3D graphene. Recently, self-supporting 3D graphene has also been produced. 3D structures of graphene can be fabricated by using either CVD or solution-based methods. A recent review by Karaman Shu et al. Have provided the summary of the state-of-the-art techniques for fabrication of the 3D structure of graphene and other related two-dimensional materials. Recently, researchers at Stony Brook University have reported a novel radical-initiated cross-linking method to fabricate porous 3D freestanding architectures of graphene and carbon nanotubes, using nanomaterials as building blocks without any polymer matrix as support. These 3D graphene, all-carbon scaffolds/foams have applications in several fields, such as energy storage, filtration, thermal management and biomedical devices and implants. Box-shaped graphene, BSG, nanostructure appeared after mechanical cleavage of pyrolytic graphite has been reported recently. The discovered nanostructure is a multi-layer system of parallel hollow nanochannels located along the surface and having quadrangular cross-section. The thickness of the channel walls is approximately equal to 1 nm. Potential fields of BSG application include ultra-sensitive detectors, high-performance catalytic cells, nanochannels for DNA sequencing and manipulation, high-performance heat-sinking surfaces, rechargeable batteries of enhanced performance, nanomechanical resonators, electron multiplication channels in emission nanoelectronic devices, high-capacity solvents for safe hydrogen storage. Three-dimensional billet graphene has also been reported. Graphene fiber. In 2011, researchers reported a novel yet simple approach to fabricate graphene fibers from chemical vapor deposition grown graphene films. The method was scalable and controllable, delivering tunable morphology and pore structure by controlling the evaporation of solvents with suitable surface tension. Flexible all-solid-state supercapacitors based on these graphene fibers were demonstrated in 2013. In 2015, intercalating small graphene fragments into the gaps formed by larger coiled graphene sheets after annealing provided pathways for conduction, while the fragments helped reinforce the fibers. The resulting fibers offered better thermal and electrical conductivity and mechanical strength. Thermal conductivity reached 1290 with m/K, 1290 watts per meter per Kelvin, while tensile strength reached 1018 Pa, 157,000 psi. In 2016, kilometer-scale continuous graphene fibers with outstanding mechanical properties and excellent electrical conductivity are produced by high-throughput wet spinning of graphene oxide liquid crystals, followed by graphitization through a full-scale synergetic defect engineering strategy. The graphene fibers with superior performances promise wide applications in functional textiles, lightweight motors, microelectronic devices, etc. Tsinghua University in Beijing, led by Wei Fei of the Department of Chemical Engineering, claims to be able to create a carbon nanotube fiber which has a tensile strength of 80 Pa, 12 million psi. I hope you guys learned something new today. If yes, then hit the like and subscribe and activate the bell icon. Thanks for watching. Stay safe and stay educated.